everyone, and this is lab 2 on the motion of a falling object. So today's mission is to try and observe and predict the motion of a pencil during free fall. Initially, my friend is going to throw down the pencil and the motion is going to be observed using tracker, and afterwards the same concept, the same motion is going to be computed on glow script using glow script code without a drag constant and then with a drag constant to then be able to graph all of these motions on one graph and see which ones were, well, which computational model was closest to the actual model of using tracker. So the Newton's second law is essential in understanding this motion because, well, it states that the interaction of objects applies an overall force on the system, affecting its change in velocity and position. And so all the interactions can be added up to get a force net to be able to then calculate the object's change in momentum and its change over time to be able to graph it. So a quick derivation of how final velocity is affected by acceleration. We can take the integral of acceleration and it will give us the area under the curve, hence the velocity of the object, but we don't use integrals in this course. So using kinematics, this is how final velocity is computed using acceleration and initial velocity, and with a small enough time interval, this can be an accurate formula. The same concept can be applied to calculating the change in position. And here it is written using kinematics. So applying this to our scenario, our initial velocity is going to be 0 and the gravitational acceleration is negative 9.8 meters per second squared. Plugging it into the distance equation, we get that the relationship between distance x and time is that the distance is proportional to time squared, the negative of time squared, and therefore we are predicting that we're going to get a parabola when there's constant acceleration with no drag force. Now testing this out using tracker, again the initial conditions are stated over here. The initial velocity is 0 as it is dropped from rest. The initial position, well, using the axes, was taking that it was 0, 0, 0, and the mass of the pencil was 5 grams. And here is the tracker's graph for position compared to time. As you can see, it is a negative parabola where with time there's a larger change in position due to acceleration. And now moving on to the computational model with no drag. The initial conditions were inputted into the code. Here is the mass, the position, and the velocity vectors, and the gravity was stated to be minus 9.8. The coefficient of drag, it was 0 because it's the computational model with no drag, and of course the equations here were changed to match those of Newton's second law. Hence, the force net was directly assigned to simply weight. Force net is only mg. And the graph the graph of velocity over time we get is a negative straight line. This is because acceleration is constant and negative, and actually in this scenario we could say that the ball would be accelerating forever. And of course the position over time, the integral of velocity over time, is a parabola as predicted by the kinematics equations, where the position increases by a factor of time squared. And comparing these two graphs, the red one is the computational model and the yellow/orange one is the model by tracker. We can see that the tracker one has a weaker magnitude. They kind of started off the same, but with an increase in time. There was a smaller change in y over the same time interval for the tracker model, for the pencil that we actually threw. That means that there's another force that is acting against the pencil to be able to slow it down, right? Which is the force of drag. So now, moving on to our second computational model, considering the drag force, it can be calculated by squaring the magnitude of velocity, as you can see here, and multiplying it by the coefficient of drag, which in our case, in an indoors environment, it was a 0.0245. As you can see here, it was inputted into the code. The equations were changed as well. Before, the force net was just equal to this area here, but now I separated the variables to make it more visual, but the weight remains the same, and the force of drag was added below, this code simulates this equation, and both of them were added to give us force net. Now this computation gave us this velocity versus time graph. Compared to the straight one of the previous model, here velocity decreased with time again, but it was no longer a linear decrease. Actually, it's sort of an exponential decay graph, where the longer the time, the smaller the change in velocity was. And we could say that if this continued for a longer time, the change in velocity would tend towards 0, reaching a concept called terminal velocity. Now comparing the three graphs, the blue line shows the computation with the drag force, and the red and orange lines respectively we talked about before. The blue line is more similar to that traced with the tracker, as you can see. This is because the conditions in the real world are not ideal. There always will be drag, in this case air resistance, and an object cannot accelerate forever like that in the ideal no drag computational model. So we've established that the real world does have drag, but even in addition to that, the drag model and the tracker model are meant to be the same. However, there's slight discrepancies where there's an overprediction in the computational model with drag as well. So when this means that when we take drag in an ideal sense, where there's constant, that means in an ideal world there's not even constant drag. So perhaps there was more air resistance, for example wind, at a certain time that caused this overprediction, or there was a tilted axis. Discrepancies in the experiment slowed the pencil down even more. And towards the end, it sped up, which may have resulted in some other tiny changes in the environment or in the system or the surroundings. So it is very important to set up the experiment indoors and on a fairly reliable setup. And finally, moving up to further questions. Well, if there's no drag, there's no terminal velocity, but the tracker model and the computational model predicted a terminal velocity, as you can see in this graph. It is tending towards a zero change in velocity. A larger distances would most probably show us a constant velocity, and then in addition to that, if pushed, the terminal velocity would be reached faster, and that makes sense because the faster object would get more air resistance proportionally at a proportional rate, hence reaching the terminal constant speed faster. So thank you, and see you in lab 3.